Let's look at a topic called combining like terms. Here's an example. If we were going to combine these terms together, we have to first think of the perspective that x is some number, but we don't really know or care what number that might be. X could be 10 or 5 or a million or -2. So one thing that we can do here is something called the distributive property. This distributive property says that when a, b, and c are numbers, these two expressions would equal each other. But it really says two things. It says you can turn an expression like this into an expression like that, but it also says the reverse, which is that if you have an expression like this, which we do essentially, that you could reverse that and turn that expression back into factored form. We sometimes call that factoring out the x. We can do that since there's an x in each term. And once we've done that, we can just use the order of operations here. 5 plus 3 is 8. And x times 8, we don't, again, know what x is, but whatever it is, x times 8 or 8 times x or just 8x would all be the same thing. These last three lines are really just different ways of writing exactly the same thing. And that is the simplified version of 5x plus 3x. Now, truthfully, most people don't often go through that work. And some people don't need to. You can just see that 5x plus 3x would equal 8x without showing any of the work. But it's nice to know where that came from. Now, we tend to think of the left side here as the problem and the right side as the answer. And while that's technically not wrong, if you're taking a test and you had 5x plus 3x, you would definitely put 8x as the answer. But a better way to think of them is, rather than think of them as problem and answer, think of them as two different expressions that always have the same value, no matter what x is. I'm just going to pick a random number for x here just to show a point. Suppose x were 10. I just kind of made that up randomly. If I substituted 10 into the left side of this equation and the right side and worked out both sides, it shouldn't surprise us that we're going to get the same answer. And there's nothing special about the number 10. The same thing would happen if I picked any other random number, let's say -2. If I plug -2 into both sides of the equation for all the x's and simplify the left side and simplify the right side, it shouldn't be surprising that I have the same answer there again. And again, there's nothing special about -2. What I am saying is that these two expressions would always have the same value no matter what x is. So earlier when I said x is some number and we don't care what it is, I really should have said x could represent any number whatsoever, and all of the math that we did there would be true. When two expressions are always the same no matter what x is, we call those equivalent expressions. You'll hear that a lot in this video. Let's take a look at another problem. Here both terms have an x squared in them. So using the distributive property, we can factor out the x squared and simplify. 4 plus 7 is 11, and some number we don't know times 11 is the same as 11 times that number, or just 11x squared in this case. Those last three lines are essentially the same thing, and that's the simplification here, once again using the distributive property. Now, if you don't need the distributive property to do this, that's fine. Some people can do these in their head and simply see that 4x squared plus 7x squared is 11x squared. But it is nice to use the distributive property because it reminds us how these rules in math operate, and it's kind of better for you if you're willing to do it that way. Nonetheless, these things are equal to each other. And again, just to show what I mean by equal, let's pick a random number for x, plug it into both sides, and show what we expect to happen, which is that we'll get the same answer twice. So random number, x equals 5. Putting 5 into all the x's on the left side and working it out should give me the same answer as plugging 5 into the right side and using PEMDAS again to work that out. And I do in fact get the same answer both times. When you're doing these problems in a math class, you're probably not going to plug random numbers in at the end, but it is a nice way to check if your expressions actually are equivalent or not. Because if they are, as they should be when you're simplifying, you should get the same answer for both, no matter what you plug in. Again, when that happens, we call these equivalent expressions. Here's a third example. As you've been seeing, we've been using the distributive property to solve these problems in a simplifying sense. And what we've been doing is we've been taking expressions like this and factoring out the common factor to make expressions like that on the left. The problem is, in this particular case, we don't have an expression in that exact format. So I'm going to use a little trick. I'm going to take the x and I'm going to replace it with 1x. As strange as that may seem, it makes sense. After all, you've known since elementary school that 1 times anything is itself. And if 1 times anything is itself, it must be true that 1 times x, or 1x, or just x are always the same. And that justifies me replacing x with 1x. But the real question isn't what justifies it. The question is, why would I want to put a 1 there? Well, by putting a 1 there, it's in the proper format to use the distributive property. Now, I want to dispel a few myths before we go on. The first myth that I hear a lot is, oh, x is 1. No, x isn't 1. X could be any number whatsoever. So if you ever hear anyone say x is 1 in these problems, that's definitely not necessarily true. These problems use the letter x to represent any unknown that we really don't care what it is. So that's false. Here's another true-false question. Does this sound better? I'll pause while you read that. As true as this may seem, and I can see an argument for it, it technically is false. There's no 1 in front of the first x. There's blank space in front of the first x. So we don't want to say there's an invisible 1, although many teachers will tell you that. It's better to say there wasn't a 1 there to start with, so I multiplied it by 1, and that doesn't change the value of anything. There wasn't a 1 in the first line, but I wanted there to be a 1 there. Why? So I could then factor out the x and properly use the distributive property. Now I can simplify by just saying 1 plus 6 is 7, and then writing it in any of the 3 last forms. It's fine as a simplification. I like the one on the bottom, as do most mathematicians. Again, when we say these are equal to each other, what we're saying is that these two expressions would have the same value no matter what number x were. And again, when that happens, we call those equivalent expressions. And finally, let's look at a problem that has many terms in it. This is a little bit more complicated, but we'll use the same principles. When I'm given a problem like this, the first thing I do is mentally identify where the terms are. Watch as I identify the terms here. Here's the first term, second term, third term, and so on. And by the way, you'll notice each term that I'm identifying, the plus or minus sign associated to its left is what counts as part of that term. Here's a term, and here's a term. So all the plus or minus signs should be thought of as belonging to the object to their right. And then what I do is I try to identify like terms. For example, I have 2 terms with an x squared, 2 terms with an x, and 2 terms without any variables at all. And what I'll do is I'll rearrange the order of the terms. You may remember this is called the commutative property, but you know it more intuitively, even if you don't know the name. We all know that adding things together gives us the same result no matter what order we add it. So by using the commutative property, I'm really just rearranging the terms. That's not going to change the total, but it will change how I do the problem. You'll notice here, by the way, that this x has no coefficient in front of it. So I'll use the fact that 1 times x is x, so that there is a number there, or a so-called coefficient. But now what I can do after having rearranged the order of the terms is I can combine like terms. I can factor an x squared out of the first two, factor an x out of the next two, and there's nothing to factor out of the last two. But this allows me to then work out what's in the parentheses and combine like terms. And after I've done that, I can do some simple multiplication. And the first times sign, anything times 1 is itself. And the rest I just cleaned up a little by rearranging the order of multiplication, which of course we know we can do. So this is the simplified version of this problem, in a sense the answer, you could say. And I recommend doing the problems this way to give yourself a solid foundation on what's actually happening mathematically here. Now at some point, whether that's today or a year from now, you will want to advance yourself to a place where you're not showing this much work. But don't push yourself, because if you start doing shortcuts too soon, you forget their meaning, and you start using shortcuts when they shouldn't be used, and that's not a trap you want to fall into. So, if you are the kind of person who would like to do these in their head, one thing that you can do is simply identify the terms that are alike, and if you feel comfortable, jump straight to the answer. Now might be a good time for you to pause the video and see if doing all this work mentally is right for you. Okay. And again, just a reminder, when we say these expressions are equivalent, what we're really saying is, if I were to pick any random number for x and plug it into all of the x's, both the left and right side of this equation would have the same answer. Again, we call those equivalent expressions.